Hello, we are back with part 2 of section 11.6, absolute convergence and the root and ratio tests. This is part of chapter 11, infinite sequences and series. Part 1 dealt with absolute convergence versus conditional convergence, and this part 2 is dealing with the root and ratio tests. So first, let's go down and play around with a little bit of factorials and what they mean. I'm going to scroll down to the last page. You want to consider doing the ratio test if your expression a sub n in your infinite series contains a factorial, which is an n followed by an exclamation point. So what is a factorial? It is the product of factorial f n factorial is equal to 1 times 2 times 3 times 4 times ... times n minus 1 times n. It is the product of all of the non-negative integers up till n. So for example, just employing that definition, 3 factorial would be 1 times 2 times 3. 4 factorial would be 1 times 2 times 3 times 4. N factorial would be the product of numbers up till n. N plus 1, because we're going to be dealing with the ratio test, is going to be 1 times 3 times 4 times 5 times ... times n minus 1 times n plus 1. And you can see here that I can, in that n plus 1 factorial, factor out that factor of n plus 1, and then I'm left with n factorial. So that's useful. Other algebraic manipulations, just to keep in mind the syntax or the punctuation of mathematics, I like to say, is if we, in the absence of parentheses, then 2n factorial is just going to be 2 times n factorial, and that's going to be 2 times 1 times 2 times 3 times 4 times ... up to n. However, if we've got inside parentheses 2n quantity factorial, then that would be 1 times 2 times 3 times 4 times 5 all the way up to 2 times n, and that's a very different number. And just to be abundantly detailed, then if you had a 2n factorial inside parentheses, then 2 times the quantity n plus 1 would be inside parentheses 2 times n plus 2. And if I factored out the 2n plus 2, I'd have 2n plus 1 factorial. If I factored out the 2n plus 1, I would have 2n factorial. And I think that that is important to note. All right, so let's go back to the problems that we have inside the ratio test. And what is that ratio test? The ratio test here states that, and we're considering a convergence or divergence of just a simple a sub n expression. And when do you want to use the ratio test? You want to use it whenever you have a factorial. So if you have an n factorial in your expression, you'll want to use the ratio test. Or if you have a 2 to the n, so if you have a number to the nth power or a number to the n plus 1 power or n minus 1 power, you might want to consider the ratio test, because you can play around with simplifying the an plus 1 over an scenario. But what is the test? We're going to be taking the ratio of an plus 1 over a sub n, and we're taking the limit as n goes to infinity. If that goes to a limit that's less than 1, we can say that our a sub n is absolutely convergent. And we say it's absolutely convergent because we're actually taking an absolute value limit. If the limit as n goes to infinity of the absolute value of an plus 1 over a sub n goes to a limit that is bigger than 1, then or it goes to a limit that's equal to infinity, and I would even say does not exist, then the series a sub n is going to be divergent. And finally, you do not get to reach a conclusion if the limit of that quotient is equal to 1. So in this scenario, you want to avoid the ratio test for a sub n equaling a rational expression, which is a polynomial or a polynomial over a polynomial, or if a sub n is a radical expression, which is kind of a false rational expression. In both of those cases, you're very likely to come up with your limit equaling 1, and you will have wasted your time in making that calculation, so avoid that. But when do you want to use the ratio test? When a sub n contains an n factorial or an a to the n, right? Where you have a number to the n, like 2 to the n. All right, so it is worth it to take a look at the proof, but in the interest of time, I'm going to show you guys how to employ the ratio test. But this does make use of direct comparison tests and also that limit and geometric series. So the very first one I think is very complicated because it involves Hopital's rule, so I want to skip ahead to part B and part C of these examples. So in taking a look at this example here, I have that this is my a sub n. So what does the a sub n plus 1 look like? That's going to look like n plus 1 factorial raised to the second power over 2 times n plus 1 factorial, right? Wherever n appears, we want to substitute the quantity n plus 1. And in simplifying that, I would get n plus 1 factorial times n plus 1 factorial over 2n plus 2 factorial. And like I mentioned before, if I factor out my factor of my n plus 1 factors in n plus 1 factorial, I get n plus 1 times n factorial. I can do it again for the second one. And then down below, I want to factor out the 2n plus 2. I want to factor out the 2n plus 1, and then I'm going to get to 2n factorial. So I know that that's what my a sub n plus 1 looks like, so that I can easily cross-cancel in my expression. So here I go using the ratio test, and I'm going to take the limit as n goes to infinity of a n plus 1 over a sub n. That's going to equal the limit as n goes to infinity of a n plus 1 over a sub n, the reciprocal, and that's going to equal the limit as n goes to infinity. And now I'm going to rewrite my expression from above, and my expression from above was n plus 1 times n factorial times n plus 1 times n factorial over 2n plus 2 times 2n plus 1 times 2n factorial. And now I'm going to take the reciprocal of 1 over a sub n, and that's going to be 2n factorial over n factorial squared. And we know that that n factorial squared is n factorial, right? And now I'm going to cross-cancel inside my absolute values and my fraction multiplication. And my fraction multiplication, I get to cross-cancel n factorial with n factorial. And then I get to cancel 2n factorial with 2n factorial. And I am left with now the limit as n goes to infinity of n plus 1 times n plus 1 over 2n plus 2 times 2n plus 1. And I want to expand that first in order to take my limit. And I get n squared plus 2n plus 1 over 4n squared plus 6n plus 2. And I can either use Hopital's rule, or I can factor out the highest power of n being n squared. But this is going to go to the absolute value of 1/4, which is equal to 1/4, which is less than 1. So my conclusion is my series a sub n converges by the ratio test, because I showed that the limit of the absolute value of a n plus 1 over a sub n is equal to 1/4, which is less than 1. All right, so with this one, I still see n to a power. I see minus 3 to the n. So if I see a number to the nth power, I can consider the ratio test as a viable way. So again, if this is my, I'm going to pause here. No, I'm not going to pause. I'm having some trouble with my pencil, and I don't want to start again. So I'm going to start again, and this is going to equal my a sub n. So my a sub n plus 1 is going to equal n plus 1 cubed over minus 3 to the n plus 1. And so my limit here, as n goes to infinity, of a n plus 1 over a sub n is going to equal the limit as n goes to infinity of n plus 1 cubed over minus 3 to the n plus 1, but then times the reciprocal of a sub n, and the reciprocal is minus 3 to the n over n cubed. And now I can start canceling my common factors. N negative 3's cancel with n plus 1 negative 3's to leave one factor of negative 3 left over. And so I end up with the limit as n goes to infinity. And now, since n is my factor, I'm going to group my n terms together, or n is my variable, sorry, over n cubed. And I'm going to group all my constant terms because the limit of a constant is a constant. And I can see I can form a composition of functions by grouping my cubed powers together. And I get the limit as n goes to infinity of n plus 1 over 3 cubed times 1 over negative 3. And I know, this should actually be n. And I also know that n plus 1 over n goes to 1 as n goes to infinity using L'Hopital's rule, or the highest power of n. So the limit of that composition is going to go to 1 cubed, which is going to go to 1. So my total limit here is going to go to the absolute value of 1 times 1 over negative 3, which is equal to 1/3, which is less than 1. So conclusion here, my series converges absolutely by the ratio test. Good. All right. So now I hope I still have this saved. When I do, I'm going to put this over. This is a little bit more involved, and I wanted to make it later because it does involve more of the L'Hopital's rule and indeterminate powers and indeterminate products. But again, I still see a factorial. So when I see a factorial, it's probably one of the only tests that you can use to determine convergence. So here I go with a sub n plus 1 over a sub n. My a sub n plus 1 does equal n plus 1 to the n plus 1 over n plus 1 factorial. And then I'm going to multiply by the reciprocal of a sub n because that is equivalent to dividing by a sub n. I'm going to factor out an n plus 1, so I get n plus 1 to the n in the numerator. I'm going to factor out an n plus 1, so I get n plus 1 times n factorial in the denominator. And now I'm going to cross-cancel common factors. The n plus 1s cancel in the top and bottom. The n factorials cancel, cross-cancel. And I'm still left with n plus 1 to the n over n to the n. If I group that into a common power, because I have the same exponents in that ratio, I do know that n plus 1 over n is going to 1, and n is going to infinity, so I'm going to 1 to the infinity. I just don't know which one's going faster, so I have an indeterminate power. Let's remind ourselves how we use indeterminate powers in L'Hopital's rule. Our next step then would be, well, let's find the ln of that expression. Let's find that limit. If it goes to a limit, then my limit's going to be e to that limit. So that's what I'm going to do next, and that's what I do over here. I'm going to take the limit as n goes to infinity of the ln of n plus 1 over n to the infinity. that allows me to use logarithmic properties to move the n down to be a coefficient. So I have n times the ln of n plus 1 over n. And if I plug in infinity, I'm going to infinity times the ln of 1 because n plus 1 over n goes to 1. And I end up with an indeterminate product. So another review of L'Hopital's rule, if you have an indeterminate product, then you could rewrite a product a times b as a divided by 1 over b, or as b divided by 1 over a. So you actually do have a choice of which factor you want to put in the denominator by raising that to the negative 1 power. But in either one of those instances, you're going to end up with your indeterminate power of infinity times 0. You're either going to end up with 0 over 0 or infinity over infinity, and then L'Hopital's rule will apply. So I choose, because of those two expressions, it's easier to take n to the denominator, call it n to the minus 1, especially if I'm going to use L'Hopital's rule and take derivatives over derivatives. So that's what I'm doing next. I'm going to take the derivative over the derivative and using the L'Hopital's rule. And the numerator derivative is still difficult no matter how you slice it. It's going to be the derivative of ln is 1 over x, but it's over what's evaluated at the inside, but then times the derivative of the inside. And the derivative of the inside involves the quotient rule. So that's what I do next. And the denominator derivative is very simple. It's minus 1 times n to the negative 2. But simplifying that expression, I end up with n over n plus 1 times minus 1 times n to the negative 2, and I still have in the denominator minus 1 times n to the negative 2. Those cancel, and I'm still left with n over n plus 1 limit, and as that goes to infinity, I end up with 1. Staying focused on what I'm doing, I'm still within indeterminate powers. That is my L. I took the limit of the ln, and the limit of the ln was equal to 1. So my limit is actually going to be e to the L, and so that's going to be e to the 1, which is e. So that tells me overall that my limit of the a sub n plus 1 over a sub n is going to e. Well, e is 2.78 ... and that's bigger than 1. So my conclusion is that this series diverges by the ratio test. So I think this is a very involved example. It does involve a lot of your understanding of L'Hopital's rule and also understanding how to use the ratio test. All right, so the root test is very similar to the ratio test. It also has a very similar proof, and I refer you to our textbook for that. But what is the root test? Again, if your limit is less than 1, you're going to converge absolutely. If your limit is bigger than 1, you're going to diverge. And if your limit is equal to 1, it is inconclusive. So that's how it is similar to the ratio test. When do you want to use the root test? You would like to use the root test when a sub n contains an n to the n expression, or or an expression in n raised to the nth power. Because if you look at the test, you're taking the nth root of a to the n, and note here that the nth root of a b to the n would equal b. And that's why if you have a variable to a variable n, you want to consider the root test so that you can get rid of at least the exponent n. All right. So in both of these cases, note in part A, we do have minus n to the n. So I'm going to use the root test in this. So this is going to equal my a sub n. So my a sub n is going to equal minus n to the n over e to the n squared. I'm going to say that that is still minus n to the n over e to the n, or I'm going to say squared, sorry. That's going to be e to the n raised to the n. And why is that the case? Because I do have that a to the b raised to the cth power is a to the b times c, and we know that n times n is n squared. Also seeing that we have similar exponents here, I'm also using the exponent rule that this is going to equal minus n over e to the n raised to the nth power. And if I do take the absolute value of a sub n, this is going to be the absolute value. And then I can actually get rid of the negative, and I'm going to say that this is equal to n over e to the n raised to the n. Good. All right, so that's my absolute value of a sub n. So now I'm going to take the root test, and I'm going to take the limit as n goes to infinity of the nth root of absolute value of a sub n. That's going to be the limit as n goes to infinity of the nth root of n over e to the n raised to the n. And remember, when I have similar exponents, then this is going to, I can get rid of the radical, and I can say that this is the limit as n goes to infinity of n over e to the n. And if I go to substitute my value of infinity, I'm going to get infinity over e to the infinity, which is going to infinity over infinity, and L'Hopital's rule applies. So here I go taking L'Hopital's rule, and that's going to be the limit as n goes to infinity. The derivative of n is 1, the derivative of e to the n is e to the n, and in substituting my infinities, I get 1 over e to the infinity, which is going to infinity, 1 over infinity, which is going to 0. So conclusion, because the limit as n goes to infinity of the absolute value of n is equal to 0 is less than 1, my series a sub n converges by the root test. All right. So this example here, again, I see an expression in n raised to the n. So I'm going to consider the root test here, and that is my a sub n. So if I do the limit as n goes to infinity of the nth root of absolute value of 5n minus 1 over 3n plus 4 raised to the n. Again, I have common roots here. This is going to equal the limit as n goes to infinity of 5n minus 1 over 3n plus 4. Those are positive values for n bigger than 1, so I don't need the absolute value signs. I can use L'Hopital's rule because it goes to infinity over infinity, or I can factor out the highest power, but in doing so, I end up with that this is going to 5/3, which is bigger than 1. So my conclusion is because the limit as n goes to infinity of the absolute value of a sub n equals 5/3, which is bigger than 1, my series a sub n diverges by the root test. Okay. So some things about absolute convergence. Both the ratio test and the root test are both tests for absolute convergence because they employ absolute value calculations. But something about the extra options you have with absolutely convergence series. So let's look at the rearrangement theorem here. It says that the terms of an absolutely convergent series can be rearranged without affecting either the convergence or the sum of the series. So let's look at, the otherwise statements. So for example, if you have an absolutely convergent series, we can add the terms in this series any way we wish, and we would still get that sum when adding infinitely many terms. However, take, for example, the alternating harmonic series. We know that the alternating harmonic series is convergent but it's not absolutely convergent. So it is a conditionally convergent series. So in taking a look at the expression, the harmonic series equal to ln of 2, we can actually find certain rearrangements of the terms. We can swap out the terms as long as we continue adding what we're adding and subtracting what we're subtracting. But in that rearrangement, we can actually force the series to converge to other values like 3/2 ln of 2, pi, or 4, etc., or even diverge. So you need to be careful. You can only really rearrange terms of an absolutely convergent series and still be sure that it's going to converge to the same sum. And that concludes it for today. Thank you very much. Next up, we'll be testing all of the series tests, strategies for series.